Okay, so welcome to lecture 9 of our this video lecture series of Physics 2. So today's discussion would be on Ohm's law. Okay, so for this discussion we will be defining Ohm's law. We will be defining DC and comparing it to AC circuits. We will have resistors in circuits, resistors in series, resistors in parallel, special case of two resistors in parallel, and resistors in combination. Okay, so let's start with Ohm's law. Ohm's law is a mathematical relationship that relates voltage, current, and resistance. This is a rule that can be applied to simple circuits having only one source. And the relationship goes like V is equal to I times R. Now, this is an idealization. When you perform or when you actually construct um, complex circuits that involves a greater number of resistances and that has an effect to temperatures and other conditions. What happens to Ohm's law between the relationship between V and IR no longer upholds. So what we see here as V is equal to IR is simply an idealization of the relationship between voltage, current, and resistance. Okay, so in this relationship, of course, just like what was presented in the earlier video lectures, the relationship that established in this equation is between V and I and between R and I. Okay, so between V and I, of course, they are directly proportional. So this means that the greater voltage that is provided by the power source, the greater the current that would be delivered through the circuit. Now, the purpose of the resistance is to oppose the direction of the current. So between R and I, the relationship is inversely proportional. The greater the resistance, the lesser the current that will be delivered through the circuit. Okay, so let's have DC and AC circuits. DC circuits are DC represents an acronym for direct current or direct current circuits. The direction of current does not change with time. This means when current is delivered through the circuit, it only has one direction. While alternating current or AC circuits, this is a type of circuit wherein the current oscillates or goes back and forth within the given circuit. Okay, so let's consider at this point resistors in a circuit. So let's have first the simple basic connection of resistors in series. Okay, so resistors in series, the current must be the same in all of them. In all resistors that are connected in series, the potential difference V sub AB across each resistor need not to be the same. So just like what we see here in this illustration, resistors in series are constructed in this manner. The, having the first resistor, the one end of the resistor is connected to one terminal of the power source. The other end of this resistor is connected to another resistor. The other end of this second resistor is connected to the other end of the third resistor, and so on. Depending on the number of resistors, we will be continuing this connection until finally we end up with the last resistor, and the terminal of that last resistor is connected to the other terminal of the power source, and this is called a series connection. Now, as a property of the series connection, the main property or main idea is that there is only a single line of flow for the current. So given this idea, therefore there is in terms of the current that are flowing through each of the resistor, the current is the same for each of the resistors. So that is why what we see here is that the current passing through the first resistor is the same as the current through the second resistor, is the same current as passing through the third resistor, and so on. Now, of course, the values for the input voltage for the whole circuit does not necessarily be the same for each of the given resistor, but is actually found by getting the sum of the individual voltage drops for each of the resistors. So, why is it that the total voltage would come from the sum of the individual voltages from the contributing voltages of each resistor? Now, this is the overall idea. The voltage V sub AB provided at the terminals point A, point B would serve as the source of the input energy for the entire circuit. Now, since this provides the entire energy source, and you have several resistors in your circuit, this means that each of the resistor would have its own share of this total input energy. So therefore, the share of energy in R1 and the share of energy in R2 and the share of energy in R3, if you're going to get the sum of those individual values of energy, that should be equal to the total input energy provided by the power source in the terminals across point A and point B. So therefore, as a property of the resistors in series, V sub 1 plus V sub 2 plus V sub 3 plus any number of voltage drops in the given set of resistors in series, if you're going to sum that up, that should be equal to the total input energy provided by V sub AB. Now, in essence, since V sub 1 is provided by Ohm's law as I sub 1 R sub 1, V sub 2 is equal to I sub 2 R sub 2, V sub 3 is I sub 3 R sub 3, and I serves as the common current. We could actually um, factor out the common current and divide both sides by that common current, so that we would have V sub AB over I total, and what is left in this the right hand side of the equation would simply the sum of the individual R's, R sub 1 plus R sub 2 plus R sub 3 and so on. Then we have V sub AB over total I on the left hand side, and of course V sub AB over I would serve as our R, or R equivalent. So therefore, in a set of resistors connected in series, in order to get the equivalent resistance, we simply get the sum of the individual resistances of each of the resistors connected in series. So therefore, we have this equation for getting the R equivalent equal to R1 plus R2 plus R3 and so on, depending on the number of resistors connected in series. Okay, so in this given sample problem, I will just be describing to you the idea of the solution, but I will be asking you to submit your solution for this sample problem. Okay, so in this sample problem, you are provided with V sub AB as equal to 18 volts. This means that the terminals point A, point B that is connected to a power source, the power source provides a voltage, input voltage of 18 volts. Although this is not drawn here in this diagram, but this should be understood. Okay, so the values for R1, R2, and R3 are the same for all the resistances, that is 1 ohm. So, of course, the value of the equivalent resistance would come from the sum of the individual values of each of the resistors connected in series. Okay, so of course that would be easy, since you are already provided by the formula for getting the R equivalent. Now the next question is, how would you able to solve for the total or the individual currents for I sub 1, I sub 2, and I sub 3? Now in order to do that, you simply need to apply Ohm's law for the overall current, which is V sub AB or over R equivalent. Once you have computed for R equivalent, you have V sub AB as 18 volts. Divide 18 volts by your computed R equivalent. That will give you the total input current in the circuit. And of course, the total input current is equal to the individual currents passing through each of the given resistors. Now, once you have computed for the individual currents, you have individual values of resistances. You could actually compute for the individual voltages of each of the resistor, so that you could answer letter B and you could answer actually letter C. Now, just to check, how would you know if your answers would be correct? If you're going to, once you have solved for the individual values of the voltages, V sub 1, V sub 2, and V sub 3, try to add them together, V sub 1 plus V sub 2 plus V sub 3. Expectedly, the answer for this sum should equal to the input voltage provided by V sub AB, which is equal to 18 volts. Since we have seen earlier that if you're going to add the sum of the individual values of the individual voltages, that should be equal to your V sub AB. If that checks out, then that means our solution would be correct. Okay, so I have only described to you the solution for the problem, but I am asking you to perform the actual solution and submit this as part of your exercises. Okay, so let's proceed with resistors in parallel. Okay, so the current through each resistors need not to be the same, but the potential difference between the terminals of each of the resistor must be the same for all the resistors connected in parallel. Okay, so the connection in parallel as an illustration, we see here, this is the type of connection for resistors in parallel. Okay, so when you say that the resistors are connected in parallel, the resistors, each of the end of the resistors connected in parallel has a direct connection to the terminal points of the power source, point A, point B. Just like what is illustrated here, R1 has a direct connection to point A and point B. R2 also has a direct connection between point A and to point B. So therefore, when resistors are connected in this way, we say that the resistors are connected in parallel. Also, if you're going to connect another resistor, for example, another resistor R sub 3 here, and we connect it directly to point B and to point A, then we say that R sub 3 is also connected in parallel with respect to R1 and R2. Okay, so since the idea is that all the resistors are connected in parallel, has a direct connection to point A and point B, therefore, whatever voltage that is provided at point A and point B, this is the same voltage that is established as the input voltage for each of the resistors connected in parallel. Therefore, whatever V sub AB is, it is the same value that is established for V sub 1, the voltage across R sub 1, and V sub 2 as the voltage across R sub 2. And if we have, for example, another resistor R sub 3 connected also in parallel, whatever value of V sub AB is, it is the same value for V sub 3 for the voltage across R sub 3. Okay, so going back, we notice here that for resistors in parallel, the voltage V sub AB is the same as V sub 1, is the same as V sub 2, equal to V sub 3, and so on, equal to any number of the voltage for any number of resistors for as long as they are connected in parallel. Now, of course, since the connection in parallel branches out, whatever current that is flowing through R1 doesn't necessarily be the same as the current flowing through R2, doesn't necessarily be the same as the current flowing through R sub 3 or any number of resistors connected in parallel. So since this is the idea that you have different values for the current flowing through each resistor, to get the total current that is provided in the circuit, we simply add them together, the current flowing through R1, the current flowing through R2, the current flowing through R3, or any number of resistors for as long as they are connected in parallel. So To get the total current, we just simply get the sum of the individual currents of the resistors connected in parallel, so that we have this expression. I total would be equal to I sub 1 plus I sub 2 plus I sub 3 plus any number of i's in the given circuit. Now, of course, if we're going to solve for I sub 1, I sub n in term, or I sub total in terms of V sub AB over R sub n, of course, V sub n, solving for I over V sub A, that is provided as equal to 1 over R sub n. If we're going to cross multiply V sub AB over I, so we will have 1 over R sub n. Of course, 1 over R sub n, uh, for the total number of resistors, we have 1 over R equivalent, or the equivalent resistance of the given circuit. So therefore, in order to get the equivalent resistance of the set of resistors connected in parallel, we simply get the sum of reciprocals of the values, the individual values of the resistances for all the resistors connected in parallel. Okay, so let's do a sample problem, or let me describe to you a sample problem. So for example, R1 is equal to R2 is equal to 2 ohms. So what would be R equivalent? So R equivalent is simply 1 over 2 plus 1 over 2. So that is 1 half plus 1 half. So 1 half plus 1 half is equal to 1. That would be equal to 1 over R equivalent. So 1 over R equivalent is not R equivalent. R equivalent is the reciprocal. So 1 over R equivalent becomes 1 over 1 gives you 1. Okay, so to further illustrate, let me illustrate that using this example. So for example, R1 is equal to 3 ohms, and R2 is equal to, say, 2 ohms. So how do you get R equivalent? So what is R EQ? So R EQ is simply okay, so the formula is 1 over R equivalent. So this means you will be getting 1 divided by R sub 3, then plus 1 divided by R sub 2, and this would serve as the sum. But this is not not equal to R equivalent. R equivalent is simply the reciprocal of the sum of 1 over R1 plus 1 over R2. This means that you will the final step of the solution is that we will get the reciprocal of the sum of the right hand side of the equal sign. So what happens is R equivalent is equal to 1 over 2. 1.2. So this means, to illustrate further, if you're going to have 1 over 3, and this would be expressed in fraction form, okay, so this is 1/3, then you should have this as your plus. Okay, so this is 1 over 2. So what you're going to do to perform the corresponding operation, mathematical operation, is to add the two fractions together. Of course, adding the two fraction means that you're going to get the least common denominator between 3 and 2, or between the given denominators. So of course the common denominator between 3 and 2 is 6. Okay, so what you do with 6 is that you have 6 divided by 3 is 2, times 1 gives you 2, then plus, of course, next is 6 divided by 2 is 3. 3 times 1 gives you 3. Okay? So you have the numerator as equal to Of course, this is equal to 5 over 6. Okay, so of course, 5 over 6, this is in fraction form. If you're going to have this in decimal form, this means that you're going to divide 5 over 6. So, meaning this would be 5 divided by 6. Expectedly, this is the same as the one we had before. This is point 8333 and so on. But still, okay, so still this is not equal to R equivalent. This is supposed to be equal to 1 over R equivalent. This is not R equivalent. As provided in the formula that is presented in the PowerPoint presentation. Okay, so 1 over R equivalent is 1 over R1 plus 1 over R2 and so on. Okay, so just like what is illustrated here. Okay, so you have 1 over R equivalent as equal to 1 over 3 plus 1 half is equal to 2 plus 3 over 6 is equal to 5 over 6 and is equal to 0.8333 and so on. The 0.8333 and so on is 1 over R equivalent, not R equivalent. So therefore, in order to get R equivalent, simply what we do is to get the reciprocal of 0.8333, which is 1 equal to this one. Okay, so next would be to get R equivalent. You get the division between 1 divided by 0.8333. Okay, so doing that, we have equals 1 divided by 0.833. And finally, what we see here is that we are given a result 1.2, just like what we see here. Okay, so again, to perform the sum of reciprocals, you get first the sum of the reciprocals of the individual values of the given fractions. So once you have done that, the final step of getting R equivalent is to get the one final step of getting the reciprocal of the result of the sum of fractions. Okay, so to get the the value for R equivalent, remember that this is only applicable for the sum of resistors of getting the R equivalent for a set of resistors connected in parallel. Okay, so last part in our discussion would be resistors in combination. Okay, so when we say resistors in combination, these are connections wherein you have a connection of resistors that are combined in series and in parallel connection. So for example, just like what is illustrated here, you have 3 resistors. You have R1, R2, and R3. Of course, R2 and R3 are connected in parallel. And the equivalent resistance of R2 and R3 would be is connected to R1 in series. Okay, so as for the second illustration, you have R2, R3, and R1. Between R2 and R3, R2 and R3 are connected in series. and the equivalent resistance of R2 and R3 is connected to with respect to R1 in parallel. So therefore, based on this illustration, in order to get R equivalent, if you have a combination of resistors, what you do is to apply the set of formulas that were presented earlier for the connection of either series or parallel to the portion of the combination to express the given connection using a single resistor equivalent to the combination, and eventually you would end up with a single resistor that would represent the whole of the combination. So this means in order to combine the three resistors, you need to combine first R2 with R3 using the set of formulas for parallel, applying the set of formulas here between R2 and R3. Now, once you have done that, you could represent R2 and R3, the R2 and R3 combination using a single resistor. And if you're going to replace this combination with that resistor and R1 would be connected in series. So therefore, in order to get the total resistance, you get the combination of R1 and the equivalent of R2 and R3 in series, so that you will end up with a single resistor representing the total resistance of the whole combination. The same goes with the second diagram. R2 and R3 could be combined using the set of formulas for series. So making this connection, representing this connection using a single resistor. So once you have done that, you could actually combine that resistor with R1 using parallel, since they are connected in parallel, rendering the combination into a single resistor that represents the total combination of the three resistors. Okay, so just like what I have illustrated earlier, you could actually connect any number of resistors in parallel. So just like what we see in this case, R1 and R2 and R3 are connected in parallel. Now, suppose they are connected each of the resistors are connected in parallel and has the value 1 ohm each, and they are connected in parallel to a power source V sub AB equal to 18 volts. So you are asked to get the value of the equivalent resistance, the value of the individual currents, and the value for the potential difference of each of the resistors V1 to V3. Okay, so this would be part of your exercise. The same goes with this figure. Okay, so you have three resistors. You have 4 ohms, 6 ohms, and 3 ohms. 6 ohms and 3 ohms are connected in parallel. So what you do is to combine these two using the set of equations for parallel. Then once you have done that, you represent this combination using a single resistor equivalent to this combination, and you have that in series with the 4 ohm resistor, and you combine these two using the set of equations for series. Then you can have the equivalent resistance, so that you could answer letter A. You are provided with the EMF equal to 18 volts, so that you could compute for the total current through the whole combination, and eventually break down this current using the set of equations for series, going back to this combination. Okay, so I will be asking also for you to solve for this sample problem as part of your exercise. Okay, so this ends up our lecture series discussion for ohms